In this lesson, we'll talk about tangent line problem and also introduce the derivative. First of all, what is a tangent line? One way to visualize tangent line is this. So imagine that you are driving on a country road, and here your head where the direction of the headlight is heading, that's where what the tangent line is. So like at this moment, this is where the tangent line is heading, right? So therefore this straight line represents the tangent line at this point. Now if you continue to drive and you drive to this location, and then this is where the headlight is pointing, and now this line is the tangent line at that moment. So here's the question: how do we actually find the tangent line? We are gonna involve the limits concept. So think about, we want to find the tangent line at this point P. This is the tangent line, by the way. And one way to approximate it is we are gonna use another point Q, and then make a line connecting these 2 points. And then when we let Q approach this P, those secant lines will eventually approach this tangent line. So therefore, here it comes that for the definition of tangent line, if f is defined on an open interval containing C, and if the following limits exist. Now let's take a look at this limit. So this limit is the ratio of delta y and delta x, where delta y represents the change in y, delta x the change in x. So when this x is approaching 0, so let's take a look at this graph. So this is the change in x. When this change is approaching 0, then this point will be approaching the point of interest. So therefore, the secant line will be approaching the tangent line. This delta y is the change in y. This is the f of c. This is f of c plus delta x. So it will be the change in y direction. And delta x is the change in x direction. So when this limit exists, then we say the line passing through C, f of C, with slope m is the tangent line to the graph of f at this point. So this limit is the slope, And how, again, from this definition, how do we find the slope of a tangent line? So we first find this quotient. And by the way, this quotient, we are going to call it the difference quotient. It's the difference of y over the difference of x, so difference quotient. Once we find this difference quotient, we are going to find the limit when x is approaching 0. So that limit is the slope. Now let's apply this concept on the following problem. So here we have the function f of x equals 2x minus 3. Let's actually visualize this function, shall we? So the y-intercept is negative 3. And when x is x over 2, the y is 0. So when x is 3/2, which is somewhere here, the y is equal to 0. And therefore, this is the line. The question is, here's the question. We want to find the slope of the tangent line when x is equal to 2. So this is where the x is 2. And we want to find at this point the slope of the tangent line. First of all, the tangent line, again, imagine that you're driving a car on this road. This is a road. And then, so where the headlight is pointing, actually, because this is a straight line, the headlight direction should coincide with this line direction, right? So therefore, I do expect the slope of the tangent line to be the same as the slope of this line, which is 2. So we look at this from a geometric point of view. Now let's look at this, find this using the definition that we just introduced, which is the process that involves limit. So the slope will be the limit, the delta x approaching 0. And here should be the difference quotient, which is f of, now here the c, this is c is equal to 2. That's where you want to find the slope of tangent line at. So we are going to say this is going to be 2 plus delta x minus f of c, which is f of 2, divided by delta x. And let's plug in those into the function. So f of 2 plus delta x will be 2 times. So we're going to plug in 2 plus delta x into the function, minus 3, minus f of 2. So what is f of 2? It is 2 times 2 minus 3. The bottom we have delta x, and this is equal to the limit delta x approaching 0. Let's simplify the top. We have 2 times 2, which is 4, plus 2 delta x minus 3, minus, let's drop the parentheses here. This becomes 4 plus 3 after we drop in the parentheses. 4 plus 3. Now we have quite a bit of cancellation in the numerator. Don't forget the denominator. So here we have 4 and negative 4 cancel. Negative 3 and 3 cancel. And we are actually left with only 2 delta x, right, on top. And the bottom is delta x. So 2 delta x divided by delta x, which is equal to 2. So therefore, this is equal to limit delta x approaching 0. By the way, 2 delta x over delta x, that will cancel. So now this limit, there's no delta x at all in this over here. So therefore, the limit of a constant is equal to this constant. And therefore, the slope of the tangent line at x equals 2 is equal to 2. That's what we discussed earlier, because we say that the direction of the tangent line coincide with the direction of the line in this case. So which is 2. That's not a surprise to us. That's what we expected. What if the function is not linear? Now let's give a try on the next one. This time, the function is x squared, which is not linear. And then let's, first of all, again, it's always good to visualize what's going on using a graph. So this is x squared. And say this is 1. When x is 1, the y is also 1. And then our goal is to find the, so this is the tangent line. We want to find the equation of this tangent line at this point. In order for us to find the equation, we need to have a slope, right? And we do have the points already. So now we just need to find the slope, and which is what we just introduced. So let's find the slope using the limits definition. Limit delta x approaches 0. Here this is f of, now the c is 1, as we want to find the equation of the tangent line when x is 1 and y equals 1 at that point. So f of 1 plus delta x minus f of 1 over delta x. And this is equal to, and we're going to plug in 1 plus delta x into the function, and which is x squared. So we have 1 plus delta x squared minus 1 squared, which is 1, over delta x. And this is equal to, let's expand it. The top is a square of a binomial, which is 1 squared plus 2 times the twice of the product, which is 2 delta x, plus square of the second term, which is delta x squared, minus 1. The bottom is delta x. And 1 and 1 cancels. And now, and then let's simplify the rest. So it is equal to 2 delta x divided by delta x is 2, and delta x squared over delta x is delta x. So we have 2 plus delta x. Now time for us to plug in this delta x, which is 0, then we're left with 2. So the slope is 2. Now let's find the equation of the tangent. So the equation of the tangent at this point, x equals 0, y equals 1, is y minus the y0, which is 1, equals the slope, which is 2, times x minus 1. So we are using the point slope form and using the results from above. And then let's simplify. This is equal to 2x minus 2. And therefore, y equals 2x minus 1. And this is the equation of the tangent line. Sometimes this situation can happen. If f is continuous at this point C, and the limits of the different quotient is infinity or negative infinity. In this case, the vertical line x equals c passing through this particular point, c f of c, is called a vertical tangent line to the graph of f. And it looks like this. Here, this f is continuous. And at c, the limit of the difference quotient is either infinity or negative infinity, then it's a vertical tangent line. We will have to find the slope of tangent line very often, and also because at different points, even for the same function at different points, the slope of the tangent line will be different. So it will be more convenient for us to define these limits of the difference quotient as a function of f, and we call this as the derivative of f. Basically, it is the slope of tangent line of f at certain point x. So if you recall earlier, we have this slope of the tangent is at c is defined like this, right? Let me quickly write it down. So if you vary this c, then you find the slope of tangent at different value of c. So if we make it general, say at point x, so at point x, then this will be the slope of the function at x. Because we need to find this so often, let's define this as a function of f. We call it the derivative of f. So here's how it is defined. The derivative of f is the limit of this difference quotient. Of course, provided these limits exist. When these limits exist, we say the derivative exists. There are a few important notes here. Let's go through those. First of all, the derivative of a function of x is also a function of x, because derivative it represents the slope of tangent line at different location of x. So if you vary the x, the slope will change. So therefore, the derivative depends on x. It's a function of x. Geometrically speaking, the derivative of f at certain c is the slope of tangent to the graph of f at x equals c. The derivative can also be used to determine the instantaneous rate of change, or simply the rate of change of one variable with respect to another. So derivative is the slope of tangent line, and slope of tangent line tells you how fast the curve is changing at that point, which is the instantaneous rate of change. And the process of finding the derivative is called differentiation. So when you evaluate these limits, you are finding the derivative. So you are doing the differentiation. A function is differentiable at x when this derivative exists at x. And it is differentiable on interval AB when it is differentiable at every single point inside this interval. A function is differentiable when its derivative exists at every point in its domain. So these are the some important points about the derivative. Now let's introduce the notation for derivative. So we have several different notations. They're all quite popular. And the first one is this f prime. We read this f as f prime because f of x is the same as y, so we sometimes write y prime. And by the way, this is actually the Lagrange notation. And dy, again, y is the same as f, so sometimes we write df dx. Dy, we usually don't read dy over dx, we just read dy dx, df dx. This is the Leibniz notation. And we also have this d represents differentiation, and this x represents the variable with respect to variable x. So this means to find the derivative of function f with respect to x. And this actually is the Euler's notation. So these are pretty popular here. In this class, mostly you will see that, but sometimes in other class, for instance, differential equation and Calc 3, then you will see that kind of notation sometimes. And you may wonder, what about Newton? Newton is one of the founding father of calculus. So Newton's notation looks like this. Y dot means the first derivative, and then y second dot, second derivative, etc. We'll talk about those higher derivative later. All right. When we using the limit notation, basically dy dx means the limits of this difference quotient, the change of y over change in x, when delta x is approaching 0, and which is equivalent to this, and all equals f prime of x. So when we say find f prime of x, that means equivalent to all these. When the derivative of f is evaluated at a specific point c, this is how we write f prime of c. That means find the derivative at c, or y prime of c, or dy dx with a vertical bar with specific value of c of x indicated here. All right, now let's do some exercises here. So this problem, you are given a function y equals square root of 2x plus 1. We're going to use the definition of derivative to find the derivative. And then we want to find the equation of the tangent line when x is equal to 4. Well, first of all, we need to find the dy dx, which means, again, we are required to use the definition. So we are going to start writing the limits notation. Delta x approaches 0, and the top is the change in y, difference quotient, right? So f of, so x plus delta x minus f of x divided by delta x. Let's start with the formal definition. Now, time for us to plug in, evaluate these two using this function here. We have square root of 2x plus 1, so 2 times. The first one is f of x plus delta x, so I should plug in x plus delta x for x, minus f of x is 2x plus 1 over delta x. So please pause the video if you want to think about how you will evaluate these limits analytically. We did something similar in the earlier lesson. So the trick here is we're going to multiply the top and bottom by the conjugates of these roots, right? The difference of the roots, then we'll multiply by the conjugates. So which will be square root of 2 times x plus delta x plus 1 plus the second square root. Of course, we should divide the same thing. And the top will have square of the first term, which is 2 times x plus delta x plus 1 minus the square of the second term, which is 2x plus 1. Divided by the bottom, we'll have delta x times the whole thing, the sum of these two square roots. All right, let's simplify the top a little here. So the top, we have 2x plus 2 delta x plus 1 minus 2x minus 1. The bottom, we have the same. It's pretty long to write, but I definitely encourage you to write the whole thing down. Okay, and at the top we should have, oops, I think the parenthesis is not placed correctly. I should place that around the sum of these two roots. And now negative 1 is cancels with this positive 1, and 2x is gone. And the top, we actually have only 2 delta x on top. And the bottom, we can see that this delta x and delta x can cancel, right? So let's cancel that as well. So therefore, eventually, this is what we have. The top, we have 2. And the bottom is just the sum of these two square roots. And then finally, let's plug in delta x equals 0. So plug that in there. And then after you plug that in, this is square root of 2x plus 1. This is also square root of 2x plus 1. So we actually have 2 square root of 2x plus 1. And these two cancels. We're left with 1. this is 1 over square root of 2x plus 1. So it's a little bit long, but it's definitely a good exercise for us to review how to evaluate the limit. But with that, this is actually so-called the derivative of this function. And when x is equal to 4, we need to find the equation of the tangent line, which means we need the slope, right? So therefore, the slope is dy dx when x is equal to 4. And then this is our derivative, so I need to plug in 4 in here. And this is 1 over square root of 2 times 4 plus 1, which is 1 over square root of 9, which is after the square root, it gives us 3. Now to find the equation of the tangent line, we have the slope, we have the x value, we still need the y value. Let's find the y value. And when x equals 4, the y is square root of 2 times 4 plus 1, which is equal to square root of 9. So y is 3. All right, I think we are almost ready to find the equation of the tangent line. So the equation is y minus 3 equals the slope, which is 1/3, times x minus 4. And let's distribute. And then we have to add the add 3 to both sides. And 3 is 9 over 3, and we have a negative 4 over 3. That means we have 5 over 3, right? So therefore, this is actually the equation of the tangent line when x is equal to 4. The last learning objective of this lesson is to describe the relationship between differentiability and continuity. So here, first of all, the derivative of f at c can be expressed in the following form, of course, provided it exists. So f prime of c is equal to limits x approaching c, f of x minus f of c over x minus c. Still the difference quotient. Here this is the change in y. You can see that f of x minus f of c, that's the change in y, delta y, right? X minus c, so x minus c, this is the change in x. The existence of the limits in this alternative form requires that the one-sided limits, the left-sided limits, and the right-sided limits to exist and equal. These one-sided limits are called the derivatives from the left and from the right. This is the derivative from the left. This is the derivative from the right. Now let's consider the following function, absolute value of x. By the way, absolute value of x, the graph looks like this, right? It's a V shape here. And we want to find the following one-sided limits. So look at the first one. This is the left-sided limits. So left derivative from the left. Now let's first plug in the function. F of x is absolute value of x minus, because we're interested what happened at 0, so f of 0, which is 0. Absolute value of 0 is 0. The bottom is x minus 0. And how do we evaluate this? X approaching 0 from the left, that means x is less than 0, right? When x is less than 0, how do we drop the absolute value sign? It is we just need to make sure that it's positive, because absolute value of anything cannot be negative, right? So therefore, but x is less than 0. To guarantee it's positive, we have to add the negative sign. So negative x will for sure be positive now, because x is less than 0. And minus 0 can be dropped, and the bottom is x. And then let's simplify it. Cancel the x, we're left with negative 1. So therefore, the limit is actually negative 1, right? Oops, I think I have missed a negative 1 here, which is the negative 1. Similarly, let's look at what we should do for the derivative from the right. So let's apply the definition, plug in the function, and this time x approaches 0 from the right means x is actually positive. Because x is positive, we really don't need this absolute value sign. We simply drop the absolute value sign. So therefore, the top we have x, the bottom we still have x, and they cancel become 1. And what's the limit of 1 when x is approaching 0 from the right? It is equal to 1. So therefore, because the left-sided and right-sided limits do not equal, therefore this limit does not exist. That means, and this is the that means the derivative, because the derivative implies both limits exist and they must be equal. Now they're not equal, therefore the limit doesn't exist, right? So limit x approaches 0, f of x minus f of 0 divided by x minus 0 does not exist. When it doesn't exist, that means it's not differentiable. Well, that actually should make sense, because the left derivative from the left here actually represents the slope of this segment, which is negative 1 in this case. And derivative from the right represents the slope from the right, and which is 1. They're not equal. That's why there's a sharp corner here, right? So this kind of tells us when you see a sharp corner, the derivative doesn't exist. So here's the theorem to before we conclude this section. If f is differentiable at c, then f is continuous at c. Its equivalent statement is if f is not continuous at c, then f is not differentiable at c. So in summary, when is a function not differentiable at the point c? Scenario number 1, f is not continuous. If f is not continuous, it's not differentiable. Second, if there's a sharp corner at c, then f is not differentiable. Third, if f has a vertical tangent line at c, in that case, the derivative is either infinity or negative infinity, which is not defined. Therefore, it's not differentiable as well. All right, let's close this section by looking at this graph. Find the values of x at which of the following is true. So the first one is G is not continuous. So let's look at inside the interval from 1 to 4. So not continuous, this is the only point that's not continuous, right? So we're going to say only at x equals 1. What about this function G is not differentiable? Well, then we have to look through all these. So this is function where it is not continuous, therefore it is not differentiable. And then there's a sharp corner here, the left derivative from the left and derivative from the right, they're different slopes, and therefore this is not differentiable. And so we've seen those two scenarios. And I do not see any place that there's a vertical tangent line here, so therefore those are the 2 points that G is not differentiable. All right, that's all for this lesson.